Morning, everyone, or good afternoon. This is Fred Schenkelberg, and welcome to the June Ensue Reliability webinar. Appreciate everybody logging in. It looks like a few more are coming in. And not sure if the sound is working all right today, so please let me know in the chat window. I've got a completely new setup today. I'm in Eugene, Oregon, where yesterday one of the kids graduated from his undergraduate program. And like most college kids these days, is trying to figure out what to do next and kind of laying some plans down and stuff. So it's kind of exciting. A little bit later today, we're going to take him and his girlfriend out for some wine tasting. So we're going to enjoy Central Oregon here for a little bit. But and thanks, George, for letting me know we're working. So if the sound's not like I typically have, hopefully it'll come through all right. And hopefully my Wi-Fi connection stays in place. So we're at a small place, and I've been kind of hoping everything works. So we'll see how it goes. I am recording it, so hopefully we'll have a good site afterwards. And also for those that are interested in the recording, thanks everyone for letting me know it sounds working. I'll have a small ebook associated with tolerance analysis that goes into more of the examples and details of that. I just, with travel in the last couple of weeks, I just wasn't able to get that formatted and finalized. But I hope this weekend I have it available and up on the Ensue site along with the recording of the session. So there should be some more material there. Also to the right of the rotating slides, there's a downloads pod that has the tolerance slides PDF, and just highlight that or select it and the download button should work. And that would allow you to get a copy of the slides if you wish that. And I'll bring it up near the end of the presentation also, so you'll have another chance to pull those down if you'd like. And if you're used to my slide sets, you know that there's not usually a lot of detail in those. Although this time I probably violated my own New Age slide set series. So there's a bit more words and formulas in it. So hopefully that'll all be useful for you. And so welcome everybody. Let me get it set up here and I've got a phone that's coming in. I want to mute it. So let me see if I can make that happen. Well, maybe I can, maybe I'm not. If you're dialing in, go ahead and please mute your phone. It looks like I'm not able to do that remotely, so I appreciate it if you did that. But let me dive into the slides here real quick, and I look forward to any comments and messages you have as we go along. And it's a little bit different topic this time than what I typically do. I'm really trying to focus on some of the tools that are important for reliability engineering. And so it should be a more interesting, well, I don't know if more interesting or not, but maybe it's something you haven't thought about with reliability engineering. So tolerance analysis, and I snuck in statistical there, so I hope I haven't scared you as I get the first slide up here. I know how much people love statistics, but and I'm still getting the background noise with somebody that's dialed in. So if you've dialed in or connecting through the phone, please mute your line. It'll help the audio quality for everybody involved. Appreciate that. And not real sure if you're hearing that or not, but anyway. So, you know, in a perfect world, we wouldn't use tolerances. We wouldn't say we need a part that's 1 centimeter long or wide, and we would just say we need a part that's 1 centimeter, and that's it. But as you know, mechanical parts and electrical parts rarely show up exactly as we specify. And so part of the design process is to say, well, how close does it need to be in order for it to be good enough? And it takes into account that not everything is going to be exactly the same. So ideally, we get a part and it fits perfectly into the system that we're building or designing. And that's what we want. It's what we really are looking for. And so that's just the design function, to acknowledge that if we get parts that are good and that we could make them exactly the same every single time, it's good for the manufacturers because we wouldn't have any fallout from our process. Everything, we wouldn't have to inspect it even. There wouldn't be any functional testing or end-of-line testing. Every mechanical alignment would be just perfect, and every component would create the circuit that we're looking for, and so on. But I'm quite sure you know that doesn't happen. But what we have is this set of tolerances that communicate what the designer wants and has, in some cases, has considered as possible between, that would still create a functional product, that the holes would still line up for a screw to mate a couple of parts, or the electronic circuit would still function and perform what it's expected to do. So there's a number of different tools that get involved here to allow us then to sort out, how do we get this balance? How do we get what is possible versus what is necessary? And I'm quite sure everybody on the line has heard of tolerance analysis, has probably worked with it in one form or another. But what I want to do is talk about it a little bit with the notion of, why we're doing it, but then also what are some of the basic tools for that, in order to give us as reliability professionals an insight to the type of information that is necessary for a design team to create really good tolerances. Now the issue is that if a designer doesn't set tolerances or doesn't set them well, we will create parts that may or may not fit within the tolerance system. So one, we have parts that are going to drop out in the manufacturing process. We're going to inspect it and they're not going to work. So we end up with yield or loss there. More importantly, though, is that, as you know, our inspection processes are not perfect. And by having parts that are likely to be outside of the tolerances and having an inspection process that's not perfect, we're likely to have parts get out to the field that either will fail fairly quickly or will increase the load or the wear or the tendency of vibration or whatever it is, that the lack of fit, the being just outside or very near the tolerance specifications, will cause a failure in the field. So you knew I was heading towards it being related to reliability, but the notion is that the tolerances is our tool to say, this is what we want. So given my stack up of, say, 5 or 6 different parts, and I need to provide a screw or a bolt that aligns these different parts, and if I make the screw holes too big to account for misalignment or variation in the parts, it may not provide that function that we need to make these various parts together. Likewise, in electronic circuits, every now and then for a timing circuit or for a sensor for reading it correctly or filtering a voltage that's coming through, we need a specific component value. And that value then would impact how the part actually performs. And if we're outside of the variation that's susceptible, we're going to end up either with an immediate failure or an eventual failure. And so those are the kinds of things that we're looking at. But it starts with one of these oxymorons, is that what we want is something that just is perfect and just fits. But what we get is what's a product of the manufacturing process. And so it's not always possible to get what we want. And, and that's all right. That happens. And a designer or somebody creating a product almost always have a sense of what the manufacturer of those components, what the variation is, what's possible. in electronic circuits, we often buy resistors that have a set tolerance. It's plus or minus 20% sometimes. But you can get a precision resistor that has a much tighter tolerance within 1%. And they cost more, and we use them where it's appropriate. Yet, whether mechanical or electrical, we usually have some notion of what's possible. Now, when you're working with a brand new supplier or you're pushing the edge of what a manufacturing process can do, then there's more unknowns. And that's where we can get involved to help quantify what is possible and what the suppliers are providing. And then later in the manufacturing process and as we go to start making our products, if it's a critical element that affects the reliability performance of our product or system, then it's a signal for places for us to monitor, to do statistical process control, to monitor and track the areas that we expect that there's variation that would be adverse to the product's performance. So there's a pretty, in my mind anyway, there's a pretty clear connection between tolerancing and our involvement as a reliability professional. So I may have just talked about all the slides I have coming up here, so we'll see how that works. But yeah, it's just a reminder to myself. And so I'm going to ask you to take a look at the chat window there, and you know, have you seen part variation lead to failure? And just a yes or no, or maybe a type of product that you saw either just normal variation or even an unexpected kind of variation. You know, this, I suspect, is not new to most of you. And it gives me a chance to have a sip of coffee here. Dimensional variation, yeah, George, we see a lot of that. Common. Yeah, thanks, Meryl, Neil. So in the material itself, interesting, George, that's much harder to measure, isn't it? Plastics, I've seen that with plastics. Just a small amount of different additives can make a huge difference. So yeah, this is nothing new to you. We're all used to heading to the boardwalk and seeing what kind of variation, what kind of issues that can happen. So what we're after is, you know, one of the tenets of a Six Sigma program, back when Motorola and to some degree GE when they did it, and you see it in some of the programs, one of the first things to do is say, well, here's my manufacturing process. Here's what's possible to create with this molding part or with this material set or whatever. And if the designer has that information, they may need to create and design a product that accommodates that full range and more of that variation. So if the specifications are well outside of what's possible, it's unlikely that we'll have variation in the normal stable process that would lead to failures. So in an ideal world, we'd be able to design products like that. But as you know, that doesn't always happen. Sometimes we get a set of components or a set of designs that one of them is going to be pushing what's possible. And that provides a natural area to focus on for quality and process control and for watching for it in reliability aspects. So that's one of the things we're after. The other part that comes into play with the reliability world is that the parts don't stay still, right? Polymers degrade, they oxidize, paints fade, and the color will drift maybe out of spec into some unwanted color, or it may stay relatively stable depending on the composition and stability of those pigments, for example. Electronics, capacitors often drift in the capacitance value because of material changes or there's a reaction to heat or abuse. Mechanical parts, they may use a CTE mismatch, or a CTE will change dimensions, or the material itself will flow or creep as it gets under load. There's all kinds of different things that our ability to just initially set the tolerances is one step. But then you add on the next layer of uncertainty or variability of that it changes with time. So between those two things, we need tolerances that are really, really wide compared to the specifications. And so it's not just the initial manufacturer and measure brand new parts and get a variation spread or standard deviation for what we get, but also how does it change with time? How does it change with use? And so ideally, right at the point when we're doing the initial design, we're involved with, well, what are the tolerances that are critical for the performance of this product? Which ones are critical because they're at the edge of what's possible to manufacture? And this is where we come in as adding the reliability element in the initial consideration is, well, what changes with time? And so that last part is often very difficult to measure. And it may involve accelerated testing and material analysis, simulation tools, all kinds of things. But it's a critical piece to understand, is the tolerance as specified adequate for the life of the product? In essence, what we're really, really after. So let me just ask it, does that make sense? Is that something you already are doing, or are many of you already involved with working with tolerance and tolerance settings? And would you expect this to be a role for the reliability professional? Yeah, thanks, Meryl. See that? Now, some of you, I recognize and know, so I'm hoping you already understand this. So hopefully what we're talking about will just reinforce what you already are working on. Yeah, George, not as much. That's how I started with this. But once I recognized the impact that I've had, I started to really focus on it. Besides, I think of my statistics I came through as wanting more data and more information. And as you fully recognize, I think everybody here recognizes that if we get involved at the point of design, of the point of decision, which includes sorting out what is the tolerances that go in the drawing or specification, that it's a lot easier to impact the reliability of the system at that point rather than at a final design review or after we go to production. It costs a lot more to do it then. Yeah, so some of us are not involved with setting that. In every system, every organization is slightly different. And I know, like in the military group, we might be, if you're overseeing the reliability of a program, you might be 3 or 4 steps removed from the people that are actually doing the tolerancing. Or if you're buying subsystems, you may not have direct interaction with those designers. So, yeah, and Jeff, it's a good point, but I think you fully realize that if it's after the fact, it's very expensive to fix it. We may have existing inventory, we may have existing systems that we may not even have the option to account for the variation. And it's a good point that it's part of the quality engineering role or maybe part of the design role. And it's part of that process of where we can influence it by adding that information, that emphasis of how it connects to the reliability aspect of it. Now, of course, yield and production yield is expensive, and we don't want to have that occur. Yet, it's even more expensive when we have a failure that occurs in the field, the system that gets fielded and starts to fail because of unwanted variation. And George, thanks for the reference for the book. I'm not familiar with that one, but I'll have to take a look at that. Thanks for mentioning it. So what I wanted to mention, and it's really not intended to make you an expert in in setting tolerances, but more so just as a quick overview and reminder, and to be able to look at what information is available in your system. So just a very quick intro to a couple different ways that are commonly used to set tolerances. Thanks, George. You know, I've heard of the book or of Kapoor as an author, but that one just doesn't ring a bell for me. So I'll have to take a look at it. So thanks. So let's take a look at how designers typically set these things up, or engineers would typically look at it. Now, worst case method, I'm sure you're familiar with, and you probably have heard of it before, and it's seen your design teams do this. This is often the first line of attack. If I can make it at the maximums of my tolerances, that the manufacturing processes for a component, say, is 1 centimeter long, plus or minus 1 millimeter, they would design their products so that they would look at the 1 centimeter plus or minus the 1 millimeter as those two maximums, and then go through the rest of the calculations, and everything else is pushed to their limits of what we expect the variation to be, and see if it still works. If it still works, if we still get alignment, or if the component still functions, if we get the right amount of wear or fit or whatever it is, then we're good. It's by far the simplest. The only thing we need is how much variation should we expect from, say, a cutting tool for cutting or stamping a part, or a mold variation, or a circuit variation, or whatever. So it's the simplest math. You just add it up at the limits. You kind of work through it as what's the worst that could happen. So it may be the maximum value or the minimum value, but it becomes, what's the most out of alignment can I get? And if it still works, you're done. That's just fine. The root sum squared method, though, is another method that's very, very common, but it takes into account that not everything in our design or in their system will be at its maximum limit. We don't have to assume that it's as bad as it can be. Rather, we say, well, we know there's variation, so I'm going to take this notion of standard deviations and say that we're not going to be at the worst case, but in general, we'll have one part that's worse at its maximum level, and another part will be at its minimum level. But in general, most parts will be kind of near their nominal value. And there'll be some variation, but in general, on average, we'll still be able to build this component and get the alignment we need. Now, what it does do is it says that the worst case won't work. But if I have 5 parts and they all have to be at the limits of what we would expect the variation to be, it's very unlikely that that would occur. So that's where we come back on to, we're taking 5 separate parts, and most of them will be just fine. And in those cases, we still get the alignment we need. We still get the connection we need. Now, the key element here is that it assumes a normal distribution. So the root sum squared method it's got a couple built-in assumptions to it, which may or may not be true. And it's one of the steps, bringing a statistician's view to it, is we'll make the measurements, understand what the real variation is, like in the worst case method. What is the actual variation versus what we think it is, or what we've been told it is? Let's go, for critical parts, let's go measure the actual variation from component to component, or part to part. And in the root sum squared method, it's using that same set of data, the actual measurements, to figure out, well, is it actually a normal distribution? Right? It's pretty dangerous to assume, in my opinion, that my tolerance, say plus or minus 1 millimeter for this component, and I have a normal distribution over that range. that happens to be plus or minus 3 standard deviation right inside my tolerance. Now, in a perfect world, that would be a barely acceptable component. Ideally, we want it to be much, much tighter than that so that the plus or minus 3 standard deviation is well away from our specifications. But it's not uncommon for most designers and most people I've worked with to say, well, I've got a tolerance and it's plus or minus some value, and I'm going to assume the manufacturer will meet that tolerance and create parts that are in a normal distribution just inside of it. That's a pretty bold assumption, right? So that's something that for me is a big red flag, and I'd say, really? Let's check that. Now, you get one of three outcomes by actually going off and making these measurements. Most of the time it doesn't really take that long. If you have a decent measurement system that doesn't have too much error. But you could find out that the designer and the manufacturer are dead on. They have a normal distribution centered in the tolerance and plus or minus 3 standard deviation right inside the tolerance. Now, personally, I've never seen that. Never observed that in practice. You could have a situation where the manufacturing process is very consistent, and you may have a nice normal distribution or some other distribution centered right on the target, and the plus or minus 3 standard deviation are well inside the tolerances. Wow, that's a moment to go celebrate. That's a great thing. Don't celebrate too loudly, because the designer may tighten the tolerances and reduce the amount of margin you got there. But it may be the right thing to do. But you want it to be very tight and well away from your tolerances. We typically use the capability index to say that that's a very capable process. The third outcome is, unfortunately, much more common, is that it's either not a normal distribution, it's clipped, or it's skewed, or it's bimodal, or it's some other shape or performance because of the way it's manufactured and inspected and sorted. Or, and, I should say or, it's going to have a significant proportion of the individual units will be outside the tolerances. And it's good to know what's our impact to yield or what's our risk for future failures. It allows us to investigate that and understand it. But it also is a message back to the designer that the tolerances in this particular circumstance are forcing yield loss and or reliability risk. So it's an opportunity to have that discussion back with your designer to open it up some. But this assumption of a normal distribution is not necessarily true just because we assume it. So it's often very well worth the effort to go and make those measurements. Now, a third method, and this one's less common in practice. I don't see it as regularly with many of the design teams. It's called the Monte Carlo method. And it's a simulation technique, and it allows us to use the actual distribution of the individual components. So if I've got, say, 5 different components that are stacking up for an alignment feature of some sort, some of them might be normally distributed. Some of them might be very clipped, and maybe they're inspected so that the tails are cut off at the tolerance level. And some of them might be a skewed distribution or bimodal, or it might be a gamma distribution or log normal or whatever it happens to be. The Monte Carlo method allows you to accommodate the different distributions. The biggest assumption is that we have good data coming into it. So either getting it from the vendors, the raw data of the actual measurements with some understanding of the measurement error, and or making our own measurements that we get reasonable understanding of the actual variation. But then it allows us to say that those 5 parts in a system is you sample you create a virtual part, or a system, I should say, a virtual system. You take a random selection from each of the 5 different components with their expected distributions, and you randomly select from each of those to create a stack up of what the virtual system as actual dimensions are. And then you make a judgment as to what its final measurement is, how well does it align, what's its a creation of those 5 parts together, what's my total length, for example. And then you repeat that process, and with random sampling of the individual components, you create a distribution of the final result of the 5 components you're putting together. And it's maybe a couple thousand different virtual systems are created that way, but you end up with a distribution that tells you that in the manufacturing process, with this disparate different distributions, I can get an understanding of what my final result will be. And then compare that to what's the final performance. Maybe it's a certain length that has to be within a particular tolerance, and you can estimate what would fall out on yield or be near the boundaries, or a hole alignment, or circuit manufacturing, or circuit board performance. So with simulation tools and with design practices, we can use this method to use the best available information from the individual components, the natural variation, and then use a simulation tool called Monte Carlo to create what's the expected output. So it has much more data goes into it, and we get much more meaningful information out of it. So it's not a system we're going to use on every program and every project and every part of our system, but in areas that we know that we've got restrictions, or we know that we got we're pushing what the manufacturers are capable of doing, or that we know that the final result, say the stack of 5 components, the final dimension is critical to the performance of our product. Those are the good candidates to go do a Monte Carlo simulation. So let's do just a quick example for one of these. So the simplest by far is that we have a stack of 5 different plates. We have different, and the overall thickness is what we're interested in. So if I've got a 25 millimeter plus minus 0.1 millimeter, the worst case analysis is pretty simple. It'd be the 25 times 5, our nominal parts, and then it's plus 0.5 for the maximum thickness that we get, or minus 0.5 for the minimum. So it'd be, is that 125.5 to 124.5 would be our range of expected final results. Now, if that's acceptable, then that's a worst case analysis, and that's just fine. Sometimes it's not. So worst case is by far the simple. But then it's just, what's the final result? What's the stack up going to be, and is that within what we're looking for? Will that allow the alignment or the performance we're looking for? So it's so simple. A lot of people don't even think through it very often. The designers do it almost intuitively. But it's quick and easy. Unfortunately, it doesn't always allow us to get to the final product we want. So the root sum squared method, we need to get this estimate of the standard deviation. And that's not always immediately available. It's rarely put on in a data sheet, for example. And then we add up the averages of the mean values of our components, and then combine the standard deviations. Now recall that we don't add standard deviations. So harken back to your old stats classroom, use the variances, add the variances, then take the square root. So it's square all your standard deviations, add those together as variances, then take the square root, and you get your standard deviation for the system back out. It's tripped up a lot of people by just adding stitching. So I just got an announcement that somebody is trying to dial in, but I have no idea if that's going out to the rest of the system, so pardon the delay there. So one way to estimate standard deviations, well, I think the best way by far is just actually go make the measurements and calculate it like we would with a standard calculator with Excel. But if you have nothing else and you need to get an idea of where you're at, is take the tolerance and divide it by 6, assuming that you've got plus or minus 3 standard deviation across your tolerance. Now, it's not always a safe assumption, yet when we have no components left, no parts at all, and we need to determine whether this particular setting for tolerance based on, say, engineering judgment and some history of, say, what's the variation of our components, it gives us a start. Then we get this value that we can then use in the tolerance stack-up. So I always kind of highlight the tolerance when we make this assumption. It's an area to go back and check to make sure that we're doing it right and that assumption is valid. So it's one way to do it. You can work with the manufacturing team or with your suppliers and get some estimate for the value. Oftentimes it's easier to make the measurement. So the notion that I don't know why I'm getting the recording there, so hopefully it's not showing up with everybody. But anyway, that's a good idea. You know, if I'm doing a prototype, especially if and as you know, we may be doing protos with different suppliers than what we typically work with. Right? So we may work with a local facility or maybe mocking up parts, or nowadays we're using 3D printers to create components to get our hands on a working prototype. And so the variation of those parts may or may not be representative of our final variation. So it's another assumption, is that will our prototype set of variations be representative of the final one? Now, in many of the high volume type products is that you work very early in the development process to work on the actual component or actual assembly lines and with your actual suppliers whenever possible. Now, of course, like for molded parts, it's expensive to cut those molds. So we may use different techniques to create those initial parts. And if in those cases, then it's harder to make the measurements because we're just not going to get them until later. So that's where these assumptions come in, is what's the expected or history of that technology, and our assumption then is it will apply in our future product. And as soon as we can get components, let's validate that. Let's make sure that that assumption is true, especially when it's really going to push the designs and the design capability. Good question. So keep in mind that the root sum squared method assumes a normal distribution. Now, a lot of parts vary and display a normal distribution. So some of the red flags is if you know that they're sorting, so like electronic components, if there's a military grade component available that's specific to the product you're using, then they may be taking out the center of your distribution. So you may end up with parts that are two different averages, one of them at -1 standard deviation, or another group that's at +1 standard deviation. So it may be bimodal because they're sampling out, inspecting out the center parts, the good parts, so to speak. Or you may be using parts that are clipped. The manufacturing process isn't capable of making parts within a tolerance, but their end-of-line inspection process then is able to discard or drop those components from what they ship you. So it may have started as a normal distribution and then been altered by inspection processes. But other types of processes that create components, like a molded part, as the mold wears, the tolerances drift. Or if a cutting tool, as the cutting tool dulls, we may get more variation in the actual dimension. Or stamping, or think of your whatever assembly process you're working with, it may not actually end up as a normal distribution. And there's all kinds of reasons for that. So thinking through how parts are made and inspected, if there's too much indication that it's not going to be normal, then you're making a pretty big assumption here using the root sum squared method. Now, in general, it's better than the worst case method, yet you can get in trouble real quick if you really are a skewed distribution on a very non-normal process. Now, the other part, and it's probably the subject of a whole other discussion, is the process needs to be stable. Right? So this is true of any of the techniques we're using, is that we're saying this part is going to be 25 millimeters thick with plus or minus 0.1 millimeters in thickness variation. And that's only true if it's stable. If every part I make is going to be within that range. So think of control charts that don't show any outliers or drift or signals that the process is unstable. Now, for practical purposes, if we're working with a new vendor that has no real track record of producing parts like that we're asking them for, it's time to think about process control, which as a side benefit provides us the data we need to estimate standard deviation. But more importantly is that if it's not stable, if we don't know what kind of components we're going to be receiving over time, it increases the risk that we are going to get parts that are outside the tolerances or bad. So I think it was George was mentioning or somebody else was mentioning material composition. If we're blending components, getting that to be stable may be critical for the load carrying capability or for the functionality of the final product. And so working through the assembly and manufacturing processes to understand, is it going to produce the same or consistent type materials over and over again? That's what we mean by stability. And the other assumption we're making is that we have minimal measurement error. Now this goes for anything we measure, right? It's again a subject that could be its own topic of measurement error and measurement system analysis. It's basic to a lot of what we do. Anything we're measuring, it's very easy to assume that we've got no measurement error. But as a quick test of your own system is get a caliper and have 3 different people make a measurement. You will see the measurement error just pronounce itself. So many of our measurement systems, whether automated or not, have some level of measurement error. There's no getting around that. But have you quantified it? Is it known? Is it consistent? And so if the set of 3 assumptions is what allows us to use the root sum squared method. But if we just wave our hands and say it's good, it's a pretty good opportunity for us to be surprised in the performance of our product eventually. So the last one here is this Monte Carlo method, and I described it briefly earlier, but one of the hard parts is, well, how many simulations do I need to do? Now, I mentioned earlier 1,000 or so, which is tedious to do in Excel. There are plugins. I think one of them is called Crystal Ball that allows you to do this. Many of the CAD software packages for mechanical folks use have it built in to their systems that allow them to do Monte Carlo approximations for their tolerancing. And some of the other simulation tools that are available, like R software, and other stats type software packages would allow us to do a Monte Carlo thing. So it takes a little bit more work or some specialized tools to look at it. But the other part is that we need to get a good estimate of the actual variation, estimating these distributions. And so the assumption is that we've got good estimates. So it usually involves getting enough parts, enough samples, or a good enough surrogates for those numbers from similar parts from a similar process that allows us to, say, have 30 pieces of data that allows us to do a basic histogram or a curve fit to is it normal or gamma or log normal or whatever, and good information from that. Now, of course, it still has to be a stable process and it still has to be minimal measurement error. But it adds this layer of complexity that we don't have with the other systems. So just a quick comparison, and then I'm looking at the clock. I've got a few minutes left, but I want to see if there's any questions of this or what's your experience with using these three systems. But here's, just a quick summary of these things. So how many of you have used the Monte Carlo method? What kind of results are you getting if you've used that? I'm not getting a lot of traction there, so I want to mention one more part. Yeah, we may have to do more work, right? We may have to get more data, do more statistics, work with designers to actually do the Monte Carlo method or even the root sum squared method. Yet what we get is more, I've been using this phrase a whole lot lately, you get a more better picture of how your final system's going to turn out and perform, right? Yeah. Yeah, Meryl, exactly right. And Neil, good to see you used it. A couple others, I'm seeing the comments now. It is a powerful method, this Monte Carlo method. And if I get a real good picture of what my final result is, and then you can do sensitivity analysis looking at which component is most critical to your final performance. It may allow you to focus resources on making sure it's manufactured to very precise or limited variation, or use a more expensive process to make the one or two components that are dominating your variation, or all kinds of different trade-off decisions are made. But it allows us then to do that, add the economics into it, whether it's a manufacturing cost or a yield cost, or if we can work it out and understand it, what our reliability costs are going to be. So it's a tool that can be used all through the process. As I mentioned earlier, it really has to start right up front. Yeah, Vipin, you're exactly right, is that for some of the CAD systems, the add-on of the Monte Carlo package can be expensive. Not everybody needs it, right? But if we can support them with using a less expensive tool or take it offline, but at least start asking those questions. And doing Monte Carlo, we can do that with almost any system, whether it's Excel, takes more work, obviously. But I'm not sure if Minitab or Jump software, Item software, some of the other packages have that capability. But in some cases, it is the right tool to use, especially when we have non-normal distributions. It allows us to get a better picture of what's actually happening. And that's what we're after. We need that information to make some fundamental decisions in the design that affects its performance. And by getting a good set of tools in place and understanding of how it works, we can then estimate yield and defect rates. And yeah, so there are tools available. There's ways to do it. it does take work. All right, last note here, and I'm not going to go through all of my slides. I have some other examples worked out. You know, at the start of the day, when a designer's sitting down with their notebook and laying out a design, it's really just engineering judgment. As a reliability professional, let's look over their shoulder once in a while and say, well, where's the assumptions here? What's the information we have or your history with, say, this molded part or this vendor or this component? What's the typical variation that we see, and what's your evidence for that? So engineering judgment's a starting point, and in many cases, it's perfectly fine. So let's ask a couple of questions to make sure that we don't have those unwanted sets of variation assumed away, and make sure we're okay. Now, in some industries, we've got standards and guidelines, and people have tabulated the variation from, say, a particular molding process or stamping process or cutting process or whatever it is. We can use that information if it's available. Question there, as you might imagine I'd ask, is, well, how relevant is it? How is the process changed over time from when these guidelines were made? So again, when it's important, when it's critical to your process, is go get the measurements, right? Go actually do the work to get the numbers you want. The one I mentioned earlier is look at sigma across your tolerance range. Now, if you know what the sigma is, if you know what the variation is, the standard deviation, that's a starting point for what the tolerance could be. So you can work this formula back from starting with the standard deviation and use that as a guide to your designer to say, hey, this is how tight your tolerance can be at a minimum. We want it bigger if possible. Or vice versa, they create the tolerance as what would work in the particular design and say that the sigma has to be at least this value or smaller. So it can go both ways, but by far the best method is just go measure it, get the values. And I think the thing you mentioned is, what if I have a prototype? Well, sometimes it's from a similar or the same process we're going to use in the final results, and sometimes it's not. So how representative is it? What is the real values I can get? But keep in mind that there's lots of sources for this data, and we're going to then estimate these distributions. Now, if they're all close enough to be in a normal distribution, the root sum squared method works just fine, and it's obvious, and it's a lot quicker. If we have variation that's not normally distributed, which is very, very common, then the Monte Carlo method is an appropriate approach. So just in summary, this is one of the sets of tools that really gives us a chance to flex our statistics muscle, but also to engage the designers on something that they're going to have to do anyway, which is set tolerances, and interact with the manufacturing process, the supplier's manufacturing process, and the final performance of our product. Other parts of your organization are probably interested in yield or cost, or cost per component or cost of the manufactured process. What we're bringing into the discussion is what's the impact of this variation on the final reliability performance of the system. Okay? It's not obvious. It rarely is an obvious connection between tolerancing and reliability. So it takes some work to get there. Fortunately, if we can design and manufacture a perfect system, we don't have any loss in yield. Manufacturing is a lot easier, and it works in the field. It's that recognition that things vary, and every component that we get will be slightly different from the other components we get, is then acknowledging that we have to deal with that variation. So I just outlined a handful of tools for doing that, but more importantly is hopefully it gave you the incentive to engage with your design teams, your engineers, on the tolerancing. Or in a design review is ask, what's the underlying assumptions and what's the supporting evidence for that? And as you're looking at products and doing failure analysis and looking for root causes of this, one of the aspects to consider, and a couple of you mentioned it, is that part variation can lead to failures. Well, let's take a look at where the tolerancing were at the start. And are they appropriate for what's capable of being produced? So it's all of those elements put together, in my mind, make the tolerance setting part as much of a engineer's, design engineer's, or development engineer's role is probably their primary on their responsibilities to set those tolerances. The quality organization of working with suppliers maybe are conduit to gather that information, but from a reliability point of view, it's our ability to influence the design when it's the least expensive to do it, such that we can make the most reliable component or system at the end of the day. So those all are parts of it. Oh, and thanks, Phil, that JUMP has the Monte Carlo method built into it. It's a little bit more of an advanced stats package, and it has some wonderful tools in it. So it's one of the many ways that we can support our teams with one of the tools that we have available. So I'm looking at my clock here, which is this cool-looking Victorian thing sitting on the wall. I think it's Victorian. My French, I'm sorry. So I've got a couple of minutes, and let me pull up the closing piece of the view of the slides. See, if you want the slide deck, you can download them, if it'll actually change for me. Maybe it's not going to go to that layout. I'm not getting it to change, so let me see what I can do. So anyway, I'll look at the questions tab or the chat window if there's any questions. And for some reason, my system is not responding there. But anyway, sorry about that. I'm not able to change the system as I would expect it to bring up the slide, the download screen. So anyway, I hope I'm still connected. What I wanted to also say is that I've been working on updating the Ensue reliability site, moving it to another platform. So those of you that are already members of the Ensue site, I'll be sending out a message about moving to the new site at some date, probably within the month. But I'm pretty excited by it because I'm planning on doing a podcast and it's a platform that I could have multiple podcasts and multiple authors for those. And I'm adding a lot more information and content there besides the webinar recordings, ebooks, and material like that. But I'm hoping to create a decent site for professional development. We'll continuing to add material to it over time, like these webinars, but also encourage you to chime in and have the discussions and so on. Let me know what you would like to see there, what more information you'd like to have, and I'd be happy to sort out a way to make that actually happen. So there's a few more slides in the slide deck here that go through some examples, but I'm not going to do that in the interest of time. And for whatever reason, my system is not going to allow me to change the view that I've got. So if you really like to get the slides, let me know, and I'll send you a link for them. And I expect to have the recording and the slides and an associated ebook that's on tolerance analysis posted probably this weekend, because I'm traveling this week. So I think that's all I've got. I don't see any questions coming in. And I'm hoping that the system is still working. My internet connection is still working. That would be nice. And maybe it's not. My session time has ended. So I'm going to end the recording. Yeah, I lost my connection. So I'm not sure if I'm still online or not, but if you can let me know. I ended the recording, and I think it's going to move to the new layout here, which has the downloads piece. You just highlight the tolerance, and then you can download that. Oh, good. I'm still online. My screen kind of froze there for a minute, so I wasn't too sure it was working or not. But, and there's also a place there if you'd really like to. You can feel free to connect with me on Twitter or LinkedIn. And if you haven't been over and joined the Ensue reliability site, there's a link there in the lower right-hand pod there, the link. You can click on that and it'll take you right to that site. So look forward to seeing you. I completely spaced out what the event is for next month, but I know I've laid out the next 5 or 6 months for it, so I know I've got something coming up, and we'll hope to see many of you again next month. So thanks for attending.